In this video, we're going to talk about continuity on a closed interval. So here's the definition for continuity when it involves a closed interval. A function f is said to be continuous on the closed interval from a to b, and remember that means we are including the endpoints a and b. If f is continuous on the open interval from a to b, remember what that means. That means we are not including the endpoints. And a function is continuous on an open interval if it is continuous at every point in that interval. But we have to talk about the endpoints differently. We can't really, a function may not be continuous at one of the endpoints, but still we would say it's continuous on the closed interval. Let's continue with the definition, and then I'll draw a picture to explain what's going on. So the second condition we need is that the limit as x tends to a from the right of f of x is equal to f of a, and the third condition is sort of the mirror image of that the limit as x tends to b from the left of f of x is f of b. And the function is said to be continuous from the right at a and said to be continuous from the left at b. Alright, so let me draw a picture to explain what's going on. Here's a number line with a and b on it. So first I'm going to draw a function that is continuous on the open interval from a to b. So we might have something kind of like this. Let's call this function f. Alright, so this function is continuous on the open interval from a to b. Now, what if I want the continuity to extend to this point, to include this point? Well, I can't make f of a up here. I can't have this jump here. Well, that would be a discontinuity. What I need is, the way I need to define f of a is to make it fit right in there. I need for f of a to be equal to whatever the y values are headed toward. In other words, the limit as x tends to a from the right. Now the function might do all sorts of things on the other side of a. Similarly over here, if I want to extend the continuity all the way to b, I would need to define f of b so that that point is filled in. Now the function may continue on like that. This function is continuous on the closed interval from a to b. If you think of, say, maybe a little bug crawling along the graph can get all the way to a and it can get all the way to b without encountering a discontinuity, a point where the function is not continuous. So the function is continuous on the interval from a to b, but we would not say that the function is continuous at a. Right there is a clear discontinuity at a, and there is one at b. So the function is not continuous at a, and it is not continuous at b. That might sound a little contradictory, but remember that what we do is we modify the definition to include these endpoints when we're talking about continuity on a closed interval. We talk about the function being continuous from the right at a, and we could say the function is continuous from the left at b. I'll write in this other fact, f of b is equal to the limit of f of x as x tends to b, but we're only talking about a one-sided limit. X tends to be from the left. Alright, let's look at another example. Here is a function that is graphed, number 1, And let's talk about the continuity of this function. Clearly there are discontinuities at -1 and at +3, but on what intervals is this function continuous? Well, and again, the graph is marked off in squares that are size 1 by 1. So this is -1, -2, -3, and so on the x-axis. So it's continuous on this interval, which would be, I think that's the episode from, sorry, the interval from -5 to -1. It is continuous on this interval. Now, again, thinking about the ant crawling on the graph, the ant can get almost all the way to -1, and it can get all the way to 3. So then there's this interval from -1 to +3, including the +3, but not the -1. And then there's this interval. You can get from x equals 3 to, well, you can go almost all the way from x equals 3 to x equals 5, just not including the endpoints. And if you want to, you can stick union symbols in there. I think I'll leave it just like it is, though. Alright, well, let's talk about number 2. You've got this function f of x, which is defined piecewise. It is defined to be 3x plus 1 if x is x is greater than 3, and x squared plus 4 if x is less than or equal to 3. So let's first think about the individual pieces. Is the function 3x plus 1 continuous, or where does it have discontinuities? Well, remember 3x plus 1, that's linear, mx plus b, it's of the form y equals mx plus b. The graph is a line, there are no gaps. So this function, if we were only looking at the 3x plus 1, there would not be any discontinuities. Now what about x squared plus 4? Well, you may remember that this is quadratic, and so its graph is going to be a parabola. And again, a parabola is continuous. So these two pieces are continuous. So we know the function is continuous if x is bigger than 3, so that would be on the interval from 3 to infinity, not including the 3. And it's also continuous on the interval from -infinity to 3, and including the 3 this time, because of the or equal to part right here. But the question is, what's happening where we change from this graph to this graph? Do the two pieces line up like that, or do we have something more like that? And how can we tell? Well, what we need to know is if the y coordinates where they join up are the same. Well, that's sort of very loosely speaking. What we need to know, what we're trying to do is figure out whether the function is continuous at x equals 3. So how can we figure out whether the function is continuous at x equals 3? Well, we need f of 3 to be equal to the limit as x approaches 3. Alright, so what is f of 3? Well, when x is 3, we're supposed to use this definition. And so if you substitute in 3, I believe you're going to get 13. So what about the limit as x approaches 3 of f of x? Well, you need to look at one-sided limits. You need to look at the limit from the right and the limit from the left. The limit from the left at 3, you'd use this part. So the limit from the left is from the left we'd be using this, that would be 13. And what about, and so far so good, what about the limit from the right? Where f of x is bigger than 3. we would use this definition. And if you, so what's the limit of 3x plus 1 as x tends to 3? I believe it's 10. So the limit does not exist. These one-sided limits are not equal. And so the function is not continuous at 3, so it's only continuous on these two intervals. The graph would look something kind of like this, I believe. Alright, let's look at our last example.